Hello. Hello. So, today we will discuss the concept of resilience and modulus of resilience. First, I will talk about this modulus of resilience. That what is this modulus of resilience is? Now, modulus of resilience is the energy stored per unit volume. This is known as modulus of resilience. So, if we draw a stress strain diagram like this, then this is y-axis, this is strain axis, and I draw stress, and here I draw strain, and then I see that what will be the area under up to the point of proportionality. Let this is the curve like this, right? So I draw a vertical line over there. Now what is the energy stored on stress strain diagram up to limit of proportionality? It is known as resilience. It is known as resilience. This is point A, this is point O. So this is known as resilience. The energy is stored per unit volume in a material is known as resilience. So the formula for this energy stored is resilience, say I am denoting it with R, 1 by 2 multiply with sigma y, because this is the yield strength up to the point of limit of proportionality, we call it the yield strength. So sigma y into multiply with the strain. This is the strain up to this point. So this is the resilience, that is the energy stored per unit volume. Now we know that stress E is equal to stress by strain. So the strain can be represented as stress by E, right? So resilience will be equal to 1 by 2 multiply with sigma y multiply with sigma y by E. So resilience will be equal to sigma y square by 2E. This is the formula for resilience, right? Resilience, not resilience, it is the formula for modulus of resilience. Modulus of resilience, right? Now, what is resilience? Resilience is the total energy, total strain energy stored in a given volume of metal within elastic limit, which may be released after unloading. This is known as the resilience. This resilience, modulus of resilience is per unit volume, per unit volume, right? They should be remembered for modulus of resilience. And for resilience, it is the total strain energy. Now how you will get the total strain energy? Actually, when we say work done, then the formula we use is the force multiply with the distance traveled in the direction of force. This is our formula. Now when we strain a material, then we will draw a load deflection diagram. This is load and this is deflection. So here I am assuming that load applied is gradually applied load. Gradually applied load. Actually, there are three kinds of load. One is gradually applied load, another one is suddenly applied loads, and third one is impact loading. Right. So here I am considering the load applied is gradually applied load. Gradually applied load is a load which is applied gradually, that is from 0 to P. 0 to P, applied gradually from 0, then 0.1, then 0.2, then 0.3 up to P. That is gradually applied load. So the load applied curve will look like this. This is the load applied and the resultant deflection over there, which is equal to this. Let this is equal to del. This is the deflection, right? Load vary from 0 to P. So what is the load? That is the force. You can see it like this, that a bar is hanging whose its own weight is assumed to be 0, and a load P is applied from which is coming from 0 to P, right? After that, this much is the deflection observed in the length of the material, right? So what will be the strain energy? Strain energy stored in this particular case will be, the load will be this force. The force will be, average force will be 0 plus P by 2. We will take the average load, multiply with that deflection which is del. So this is equal to P by 2 into del. This is the energy stored, total energy stored in the material under the application of load, and this is known as resilience. Total energy stored per unit volume stored is known as modulus of resilience. Now we know that this is known as modulus of resilience and this is known as total. If we multiply this particular value with the volume, then we will get this particular formula for particular volume, right? That can be explained in another example. Now let us see how this particular concept is useful. Now if greater is the modulus of resilience, then greater will be the spring back action. Now we use the springs. In springs we use the material spring steel whose carbon percentage is more than 0.6%, right? Spring steel. Now if I apply some kind of load, the spring is compressed. However, strain energy is stored in the material. So what kind of material should we utilize to make the spring? This is a question. The spring should be made of a material, the wire of the spring should be made from such a material whose sigma y is more. Now in case of high tension steel, the sigma of high tension steel is greater than sigma of mild steel. We already know in our previous video that this was around 1100 megapascal and this value was around 250 megapascal. So the resilience of sigma HTS will be more. So the resilience is sigma y square by 2E, right? And E is same for HTS also, for sigma ms also. E is same, but sigma y for HTS is more. So the resilience of this particular material is more. So this is more favorable condition for designing spring. However, there are some other conditions are also for designing the spring. So the steel of the material of this spring should have more modulus of resilience. So now you are able to understand that what is modulus of resilience and what is resilience and what are the difference between two and why modulus of resilience is important. Thank you.